Hello and welcome to Programming Like It's 1979. Today we're going to be spending some time in the Apple II Machine Language Monitor. Recently, someone asked on one of my videos about 6502 assembly language programming, why are the status flags a really complicated topic? It's a good question. The status flags are the type of thing that are simple once you understand them, but seem sort of obscure until you've used them in anger. As Louis Sander said in a 1984 issue of Compute magazine, quote, "Like almost everything in ML programming, the flags operate in a straightforward and unambiguous way, but they are full of mystery for the beginner," unquote. Let's break them down and see if we can explain them. We're going to hop into the Machine Language Monitor.
Each of these operations, record keeping and accounting, control, design, and simulation, is achieved through the manipulation of numbers according to instructions and rules given to the computer by the programmer. But what are these rules, and what is the relationship between numbers and the real things they are said to represent?
There are three fundamental reasons the status flags are weird. They're opaque when you're not writing code, often being presented as a unit. They have differing semantics, with some being set as side effects of instructions and others being set explicitly by the programmer. And lastly, some of the flags deal with obscure issues that many programmers will hardly ever encounter. We can inspect the flags by typing Control-E and then return in the monitor, and we get some information here. The values of the A, X, and Y values, for example, and the P equals 00 is telling us what the processor status flags are set to. Right now, they are all clear, which is great. Throughout this video, when we want to translate what this p-value means, since it's being presented to us as a hex number, we'll just hop into the calculator and type the number in. So for example, with 0 in the calculator, or 0 hex that is, we can see that the rightmost 8 bits are all 0, as are, in fact, all the rest of them. The status flags are almost always treated separately, but structurally occupy a single byte of the 6502's memory. We can think of them as a status register that can take one of a number of values. But in practice, we use the abbreviation NV-BDIZC to remember them, although frankly it's not that great a mnemonic. That abbreviation describes what each register represents, from the most significant or leftmost bit to the least significant or rightmost bit. Let's approach them in that order. The leftmost flag, N, stands for negative. This flag will match the high bit of the result of whatever operation the processor just completed. So if we load FF into a register, the N flag will be set. Let's try this. We're going to write a very small machine language program. A9 is the mnemonic for load A. We're going to load FF into it. We could put a bunch of FFs after it just to keep the listing clean. Let's take a look. You know what? Let's add a break here. Let's add a break instruction at address 802. That's much better. Now we can run it. And we can see our processor status flag is B0. If we type that into our calculator, we see that bit 7 is set to 1. So this is a negative value. Bit 6, which is the next bit to the right, is the V flag, which stands for overflow. In order to understand this, you need to understand a bit about 2's complement arithmetic. We discussed this in some detail in our arithmetic logic video. We also implemented some 2's complement circuits in our arithmetic logic lab, and we also implemented an overflow bit, as well as some of the other status bits that we're talking about today in our arithmetic lab video. And we're going to configure this splitter. As input, it's taking 16 bits, and as output, It's going to output 2 buses. One of them is going to have 15 wires, which we're going to ignore. And then the 16th wire is the one we actually want. So we're just going to go ahead and route this that way. And then this is a straight shot right there. And that, I believe, that's the NG flag. We're just literally looking at the most significant bit. Since we're using 2's complement arithmetic, if the most significant is 1, we know the number is less than 0. This flag is used for signed arithmetic. It's set whenever there's a 2's complement overflow. So, for example, if we load the value 7f, which is positive, into the accumulator, and then add 1 to it, and run this program, you can see there we're loading to the accumulator. Yes, that looks right. We're going to run it, and we can see that the processor status flag is F0. So that F represents the leftmost 4 bits in our byte, and they are all 1, 1, 1, 1. Therefore, bit 6 is 1. Bit 5 is the dash in our mnemonic. It has no use, and it is always set to 1. Bit 4 is the break flag, which is set whenever a break BRK instruction is executed. Since I'm exploring these status flags with you by just typing in small programs that end in break, it's always going to be set in this video. Moving to the right, we hit the D flag. Unlike the other flags, this isn't really a read status. It's meant to be set by the programmer. If you set the D flag high, all of the arithmetic in the CPU is done as BCD, or binary coded decimal. Even in the 1980s, hardly anyone used BCD, so you will rarely have to deal with this flag. Your main concern is making sure that you don't turn it on accidentally. Bit 2 is the interrupt mask. Turning this on will make the computer ignore all non-maskable interrupts, such as scanning the keyboard. This is another flag you definitely don't want to set accidentally. Bit 1 is the 0 flag and is probably the one you will use most often when programming. So let's load a 0 into the accumulator, follow it up with a break. Let's take a look and run it. We can see that our processor status flag is 72. 72 hex. Bit 1 is the second bit from the right. It will always be set when our value is divisible by 2, so we can see that it is in fact set here. Lastly, our rightmost flag, bit 0, is the carry flag. Whenever an operation causes the result to roll over from FF to 00, or in the case of certain operations, such as add with carry, the flag will be set. Let's load in FF to the A9, to the A register, and then add a number to it. And we can see here that the processor status flag ends in 1. This flag can also be manipulated directly with the SEC set carry or CLC clear carry opcodes, and you'll be doing this quite a lot if you're doing almost anything involving arithmetic. So that is the 6502 status register. As you can see, each individual flag in the register is pretty easy to explain, but it's such a grab bag of assorted topics that I didn't really want to dive into it in detail in the middle of a beginner's introduction to machine language. This demo, by the way, written in BASIC, is by Dieter78 on Twitter. Thanks for making it. I hope you enjoyed taking a closer look at the 6502 processor status flags with me. This has been Programming Like It's 1979. Thanks for watching.